Welcome to PrimeStar Automotive. Whether you're an automotive student, apprentice, technician, or enthusiast, you're in the right place. Let's learn together. We are going to use this vehicle as our test subject for this brake system lesson. For the purpose of learning, we have to make the vehicle transparent so we can properly see the locations of the brake systems and components. To further aid our study of this lesson, I have here the individual parts of the brake system for familiarization purposes, which is a very important part of this lesson. An automotive braking system is a primary safety mechanism engineered to convert kinetic energy or vehicle movement into thermal energy, which is heat, via controlled friction, ultimately bringing a vehicle to a stop or maintaining its speed. Fundamentals and physics of braking. An automotive braking system operates on three main physical principles: Pascal's law, mechanical and hydraulic advantage, and frictional energy conversion. Pascal's law: pressure applied to an enclosed incompressible fluid is transmitted equally and undiminished in all directions throughout the fluid. In a vehicle, pressing the brake pedal generates hydraulic pressure, which is transmitted throughout the brake circuits to the wheel calipers or wheel cylinders. The resulting force at each piston depends on its surface area. Pascal's formula applied: pressure equals force over area. Mechanical and hydraulic advantage. A small force applied by the driver's foot is multiplied twice. First, mechanically by the brake pedal lever arm ratio, typically 4:1 to 6:1, and then hydraulically by the surface area ratio between the smaller master cylinder piston and the larger wheel cylinder pistons. And energy conversion. A moving vehicle possesses kinetic energy. This is calculated using the formula. This means that kinetic energy equals 1/2 of the vehicle's mass multiplied by the square of its speed. During braking, friction between the brake pads and rotors, or between the brake shoes and the drums, converts this kinetic energy into thermal energy. The resulting heat is absorbed by the braking components and then dissipate into the surrounding air. Under similar vehicle braking and road conditions, braking distance increases approximately with the square of the vehicle's speed. Therefore, if the vehicle's speed doubles, the kinetic energy that the brakes must absorb becomes 4 times greater, and the braking distance may also become approximately 4 times longer. To illustrate the force path of the brake system, I highlighted the components. Hydraulic actuation and pressure generation overview. Hydraulic subsystem acts as the muscular backbone, transferring mechanical pedal force to the wheel units. For a better understanding and familiarization, I have labeled the hydraulic subsystem components of the brake system. Power brake system, force flow. Begins with the driver pressing the brake pedal. The brake pedal serves as the primary human-machine interface. It provides initial mechanical force multiplication via a pivot pin and lever arm. Connected to the pedal pin is a push rod that extends into the power brake booster. Power brake booster. Because human foot pressure alone is insufficient to stop a 1,500 to 2,500 kilogram vehicle quickly, power boosters amplify pedal force. The power brake booster uses vacuum booster. Brake booster uses engine intake manifold vacuum or a vacuum pump in diesel or turbocharged engines against atmospheric pressure separated by a flexible rubber diaphragm. When the pedal is depressed, a poppet valve admits atmospheric pressure to one side of the diaphragm, creating a pressure differential that pushes the master cylinder pushrod with forces exceeding 1,000 Newton. Hydroboost systems used in heavy-duty vehicles or applications lacking consistent vacuum manifold. It utilizes pressurized fluid from the power steering pump to provide assist. Note: this topic will be covered in greater details in future advanced lessons. Electro-hydraulic boosters or e-boost. Common in modern electric vehicles and hybrids, an electric motor drives a piston to generate hydraulic pressure on demand without relying on engine vacuum. Note: this topic will be covered in great details in our future advanced lessons. Tandem master cylinder. The master cylinder converts mechanical pushrod force into hydraulic pressure. Modern vehicles uses a tandem master cylinder with two separate internal pistons, primary and secondary, operating within a single bore. Dual circuit safety. If a brake line leaks or one hydraulic circuit loses pressure, the remaining circuit can continue operating and provide partial braking capability. Pedal travel may increase and overall braking performance will be reduced, allowing the driver to slow and stop the vehicle with greater effort and a longer stopping distance. Circuit split configurations. Front/rear split. One circuit controls both front brakes, the other controls both rear brakes. Common in rear-wheel drive trucks. Diagonal split or X-split. One circuit controls the front left and rear right brakes, while the second controls the front right and the rear left. This prevents severe vehicle yaw or spinning if one hydraulic circuit fails. Brake fluid and fluid reservoir. Reservoir sits directly at the top of the master cylinder, supplying brake fluid and accommodating fluid level changes caused by brake pad wear or thermal expansion. Brake fluid ratings. Hydraulic fluid must maintain a high boiling point and low viscosity across extreme temperature ranges. Crucial characteristics of brake fluid: glycol-based brake fluids. .3, 4, and to 5.1 are hygroscopic. They absorb moisture from the air over time, lowering their boiling point and leading to internal corrosion or pedal softness if not flushed regularly. Wheel end assemblies. Wheel brake assemblies apply friction directly to the rotating wheel hubs. Disc brake system. Single piston floating disc brake caliper and rotor assembly. Disc brakes offer superior heat dissipation, fade resistance, and self-cleaning performance compared to drum brakes. Bolted to the wheel hub, rotors rotate at wheel speed. Different types of brake disc or rotor disc. Solid rotors. Solid cast iron disc used primarily on lighter rear wheels. Vented rotors feature internal cooling vanes sandwiched between two disc faces. Centrifugal force pulls cool air through the center hub and expels heat outward through the vents. Slotted and drilled rotors. Slots sweep away brake pad dust and gas buildups. Cross-drilled holes reduce mass and release trapped gases. Through drilled rotors can develop stress cracks under track conditions. Carbon ceramic rotors, made from carbon fiber, reinforced silicon carbide, ultra lightweight, operating above 1000 Celsius without thermal fade, found on high-performance sports cars. Brake calipers. Caliper housing straddles the rotor and houses hydraulic pistons and brake pads. Floating or sliding calipers uses one or two pistons located strictly on the inner side. When pressurized, the piston pushes the inner pad against the rotor. The resulting reaction force pulls the caliper frame along guide pins, pulling the outer pad against the opposite rotor face. Fixed calipers. Fixed rigidly to the suspension knuckle without sliding pins. Opposing pistons are 2, 4, 6, or 8 pistons push pads simultaneously from both sides, yielding stiffer pedal response and uniform pressure distribution. Disc brake system. These brake systems offer superior heat dissipation, fade resistance, and self-cleaning performance compared to drum brakes. Brake pads. Consist of a steel backing plate bonded to a high friction material block. Types of brake pads: organic, soft, white, low rotor wear, but wear quickly and fade under heavy heat. Semi-metallic, 30% to 65% steel, copper or iron fibers. Excellent heat dissipation and durability, but noisier and produces noticeable metallic dust. Ceramic, dense ceramic compounds with embedded copper and non-ferrous fibers. White, low dust, long life, consistent performance across wide temperature windows. Drum brake system. Drum brakes are cost-effective, self-energizing units commonly found on the rear wheels of economy vehicles or light trucks. This image represents the hydraulic drum brake system. Cast iron housing attached to the wheel hub that rotates around the internal components. Wheel cylinder. A dual piston hydraulic slave cylinder mounted at the top of the backing plate. Hydraulic pressure forces two opposed pistons outward. Brake shoes. Arc-shaped steel plates lined with friction material. The outward movement pushes them against the inner circumference of the spinning drum. Self-energizing action. As the leading shoe contacts the spinning drum, the drum's rotation drags the shoe into the anchor point, wedging it tighter against the drum face and increasing stopping power without additional hydraulic pressure. Here is an overview of a drum brake self-energizing action. I want you to be familiar in this one because this is very relevant when you are doing repairs or diagnosing. Return spring and star wheel adjusters. Return springs have alternate and specific names. For now, just be familiarized with them, and I will cover this in great details in our advanced lessons in the future. Return springs are mechanical spring pulls shoes away from the drum when pedal pressure drops. Star wheel adjusters automatically extend as shoe wears down to maintain constant gap between shoe and drum. Return springs are mechanical tension springs that pull the brake shoes away from the drum when hydraulic pressure is released, restoring the correct shoe to drum clearance. Star wheel adjusters compensate for brake shoe lining wear by gradually extending to maintain the correct clearance between the shoes and the brake drum. Introducing electric brake control and safety system. Modern vehicles use electronic sensors to continuously monitor driver inputs and how the vehicle is actually moving. The sensors send this information to the ABS/ESC control module. If the module detects wheel lock-up, excessive wheel slip, or loss of vehicle stability, it controls the solenoid valves and electric pump within the hydraulic control unit. The hydraulic control unit can increase, hold, or reduce brake pressure at individual wheels within milliseconds. This helps the driver maintain braking control, steering control, and vehicle stability. So here is the logic of how the electronic brake control and safety systems works. The sensors, the individual wheel speed sensors, steering angle sensor, yaw and G sensor, continuously sending signal to the ABS or ESC module. Then the module decides based on the driver's command, demand, and intention with the actual vehicle movements. And the hydraulic solenoid valves act or respond either increase, hold, or reduce brake pressure. The result, brake pressure is adjusted at the affected wheel to help prevent wheel lock-up, skidding, and loss of vehicle stability. Note, we are going to discuss in great details about the ABS ESC in our advanced lessons in the future. Modern automobiles integrate electronic sensors and solenoid actuator to modulate hydraulic line pressures automatically in milliseconds. The ABS or anti-lock brake system prevents wheel lock-up during emergency braking, enabling the driver to maintain steering control. Wheel speed sensors is a Hall effect or magnetic inductive sensors continuously monitor rotational speed at each wheel hub. Here is what a wheel speed sensor looks like in actual. The wheel speed sensor monitors the rotational speed of each wheel and sends this information to the ABS/ESC control module. By comparing wheel speeds, the control module can detect if a wheel is beginning to lock, slip, or spin, allowing it to adjust brake pressure and help maintain traction, steering control, and vehicle stability. Electronic control, or ECU, is located in combination with the HCU, or the hydraulic control unit. The ECU detects rapid wheel deceleration indicative of imminent lockup, and it is integrated with the HCU. Hydraulic control unit contains high-speed solenoid valves, normally open and normally closed, along with an internal pump. It cycles pressure through 3 phases up to 20 times per second. Hydraulic control units' 3-phase functions are: number 1, press hold, valve closes line to prevent further pedal pressure from locking the wheel. Number 2, pressure release, dump valve opens, releasing pressure to the internal pump accumulator. Number 3, pressure increase, pump forces fluid back into the line to reapply braking force once wheel traction returns. Electronic brake force distribution, or EBD. The EBD dynamically adjusts front to rear brake force ratio based on vehicle weight transfers, payload, and deceleration rates. Because weight transfers forward under heavy braking, electronic brake distribution limits rear brake line pressure before ABS triggers, preventing rear wheel lockup and maximizing stability. Note, this topic will be covered in greater details in our future advanced lesson. Traction Control System, or TCS. TCS detects individual wheel spin during acceleration and selectively applies the brake to the slipping wheel while reducing engine throttle, transferring power to the wheels with grip. Electronic Stability Control, or ESC. ESC uses steering wheel angle sensors, lateral acceleration sensors, and yaw rate sensors. If the car understeers, plows straight, or oversteers, it swings rear out. ESC selectively brakes individual wheels, example inner rear wheel during understeers, to force the vehicle back onto the intended path. Note, TCS and ESC will be covered in greater details in our future advanced lesson. Electronic Parking Brake, or EPB. EPB replaces traditional mechanical handbrake cables with small electric servo motors mounted directly onto the rear disc brake caliper. When activated via a switch, an electric motor turns the worm gear, driving the caliper piston forward against the rotor. Parking brake. Here's an actual parking brake look like. Manual parking brake is a mechanically operated system used to hold the vehicle stationary when parked. When the driver pulls the hand lever or operates a foot brake, the movement is transferred through steel cables to the rear brakes. The cables operate a lever mechanism that either expands brake shoes against the inside of a drum or mechanically applies the rear disc brake calipers. A ratchet mechanism holds the parking brake in the applied position without relying on hydraulic pressure. When released, return springs allow the brake components to move away from the drum or the disc. Now we have reached to the knowledge application. This is where you check your understanding. So read carefully all these questions here and apply the knowledge that we have discussed here, and the answers will be revealed in the next slides. And here are the answers to the questions previously provided. Read through, go back to the lessons if you have to, and I hope you learn something. Thank you for joining this lesson. We at PrimeStar Automotive hope that you found it informative and valuable. Whether you're an automotive student, apprentice, technician, educator, or enthusiast, we appreciate you being part of our learning community. Continue learning, continue improving, and we look forward to seeing you in the next lesson. Subscribe for future lessons in the Automotive Fundamentals series. Thank you.